When finding the probability of the union of two events, we can use this formula. So it says if you're given events E and F, the probability of something occurring in their union is equal to the probability of event E occurring plus the probability of something in event F occurring minus the probability in their intersection. So let's say that we are given the sample space, the numbers 1 through 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is our sample space. If event E is an odd number, 1, 3, 5, 7, 9, and event F, say, is our multiples of 3, multiples of 3, let's say, 3, 6, 9, we want to know, and we wanted to know the probability of the union of E and F, right? The probability of the union of E and F, probability of E union F. Well, that would be the probability of something in event E occurring. So there's 5 out of our total 10, 5 out of 10, plus the probability of F occurring, so that's 3 out of 10, minus the probability of something in their intersection. So we can see that both a 3 is in both and a 9 is in both, so that's 2 out of 10. So 5 plus 3 is 8, minus 2 is 6/10. So we end up with 6 out of 10, or 3/5, a 3 and 5 probability. We could have put all of this together, right? We could have put all this together and ended up with, if we were looking at just the union of these two sets, our union would be 1, 3, 5, 6, 7, and 9, which would be a total of 6 elements out of our 10 in the sample space, and we would get the same result here, right? But let's say we were looking at a different two events. Same sample space, but different two events. Maybe our two events now are E is picking a number 1 through 4. 1, 2, 3, 4. And F was picking a number, just a 9 or a 10. So if we wanted to calculate this union, right, the probability for this union, it would be 4 out of 10 plus 2 out of 10 minus the intersection. But there's nothing in the intersection. 1, 2, 3, and 4, none of those elements exist in F. So we would be calculating a probability of 0. Now, if you have two sets that contain no elements in common, we say that those two sets are mutually exclusive. Mutually exclusive. This event and this event have nothing in common, so we say that they are mutually exclusive. So that says if events E and F have nothing in common, they're mutually exclusive. And if we're trying to calculate the probability of the union of two events that are mutually exclusive, then it ends up just being the probability of your first event plus the probability of your second event. But when we subtract their intersection is actually just equal to 0. So we don't even have to subtract the intersection. It's just going to be this for the union of two events that are mutually exclusive. You just take the sum of the two probabilities of your two events. The complement of an event is defined to be the set of all outcomes that are not in our given event. So if we have some event E, then we say E bar with a bar over it is called the complement of the event, and again is the set of all outcomes that are not in our event E. So let's say that we have some sample space. Maybe we're just rolling a die. 1, 2, 3, 4, 5, 6. So if we wanted to say that our event E was rolling an even number, 2, 4, or a 6, we know that its probability is 3 out of 6. We could calculate the probability of its complement by taking the total probability, 1, and subtracting the probability of this event E. Now, when we're talking about the complement for this event, E bar, is just any element that is not in E. So if E is just the even numbers, 2, 4, 6, its complement would be the odds, 1, 3, 5 from our sample space. But if we're calculating the probability, we can do it one of two ways, right? So the probability of the complement is equal to 1 minus the probability of the actual event, which is 3/6, which ends up being 1 minus 1/2, or 1/2. Now, that's if we're using this formula. For this example, we don't actually have to use this formula because our sample space is pretty nice and finding the complement was pretty easy. But we can see that the probability of the complement is just 3 elements out of the total of 6, which ends up being 1/2. So using the formula and actually just calculating the probability in the normal way that we end up with the same result. And this is going to be true anytime you're trying to calculate the probability of some complement.